Welcome to this afternoon session on semantics. We'll have 4 talks. And the first one is by Philip Dufter.
All right, thank you very much and welcome to the afternoon session. So I'm going to present the paper Analytical Methods for Interpretable Ultradense Word Embeddings. My name is Philip, and this is joint work together with my supervisor Hendrik Schütze from LMU in Munich, Germany. So let's jump right in. Word embeddings is a concept which is used, essentially everywhere in NLP. Let it be it as the first layer of a neural network or standalone as like pre-trained word embeddings. Just for notation purposes, we use it as a mapping function which maps words into a d-dimensional vector space, or we denote it as a matrix E, where the rows are essentially the d-dimensional vectors for each word. So word embeddings are very useful, however there's also some drawbacks. For example, they are most of the time not interpretable. By interpretability we mean that individual dimensions can correlate with some linguistic feature. For example, if the first dimension is higher if the sentiment is positive or lower if the sentiment is negative, then we would call this interpretable in our definition. And that's desirable for several reasons. So, for example, to retain relevant information, to discard unwanted information, for example, bias information. And it also supports the goal of having interpretable neural networks when it's used as the first layer of networks. So there's 2 possibilities to obtain, generally speaking, 2 possibilities to obtain interpretable embeddings. So one is to invent an embedding algorithm which yields interpretable embeddings by itself. An alternative is to use or consider pre-trained embeddings and just find transformation or rotate the embedding space such that the dimensions are actually aligned with linguistic features. We focus on the latter one, meaning we have our embedding space E and we search now a linear transformation Q, actually a linear orthogonal transformation Q, which rotates the vector space. So note that with an orthogonal transformation, this whole operation is distance preserving, so we do not change any properties of the embedding space. Then by simple matrix multiplication we can get E dash, which is kind of an interpretable space. The advantage is we do not change the space, so downstream performance is maintained. Disadvantage is that we assume that the interpretable directions exist already in the original space. So if it's not there, we also can't find it. So as a quick simplification, just to make the formulas a bit easier, we now, instead of rotating the whole space, we now focus on simply identifying a single direction in the embedding space which is interpretable, meaning we search for a vector Q, which is essentially a one-dimensional subspace. But most results generalize to multiple dimensions. So to give a quick overview of our system, we use pre-trained embedding space E. We use a linguistic features input, for example, a sentiment lexicon, which assigns positive or negative sentiment scores to words. Then we have some model which gives us back our interpretable dimension Q. And by projecting the embeddings onto this dimension, we can get interpretable values, for example, sentiment scores for the whole lexicon. Obviously, this idea is not new, so there exists a huge range of work in this area. One work we particularly focus on is the densifier model by Rota et al. 2016. And the intuition is that, you minimize the distance between words with the same label, for example, the same sentiment label, and you maximize the distance between words with different labels. And then you find your rotation matrix Q and get a modified space. The actual objective function, which is optimized by densifier, is shown here. It does exactly what I just said, maximizes the distance between words with different labels and minimizes the distance between words with the same label. And so that's a nonlinear optimization problem, which is suggested to be solved with gradient descent by Roth et al. And in order to obtain an orthogonal matrix, if you want to consider multiple dimensions, you need to do re-orthogonalization throughout the gradient descent. We actually propose that if you do like small modifications, you use the square Euclidean norm, then a simple closed form solution becomes available and you don't need to use any optimization at all, but you can obtain your solution by simple Eigen decomposition of a matrix. So how does that work? It's actually just exploiting the associativity of matrix product. So we use our original objective, we reformulate it, and we come to the problem shown at the bottom, which is actually just the Rayleigh quotient of Q with respect to the matrix A. And the solution is simply doing an Eigen decomposition of the matrix A, which we defined here. The beautiful side of it is if you do it like for multiple dimensions, our matrix A is real and symmetric, and then by definition our matrix Q is always orthogonal. So we don't need to apply any heuristic in order to orthogonalize it. So now we also want to verify whether this modification works. So we work on English and evaluate on 3 different tasks. So the first one is sentiment lexicon deduction. So we have an embedding space, and we assume that for the blue vectors we have sentiment labels available. We use our system to obtain a transformation, a rotation, such that the x dimension here becomes actually interpretable. Then if we project our vectors onto the x dimension, we get scores for all words in our embedding space. We use those values as predicted sentiment scores, and we can compute, for example, Kendall-Stauber rank correlation with a goal lexicon. If we do that, we show here a macro mean across 8 different lexica. Then we can see that densifier and dense ray perform the same. That's expected. We use essentially the same objective, slight modification. The only difference is that dense ray uses a closed form solution and densifier is optimization based. Actually, we also computed SVMs as a baseline, and they perform way the strongest. So I guess that's a surprising result. Simple methods perform often the best. You might ask now, why use dense ray at all? So it's actually more robust than densifier. The densifier algorithm, you have a gradient descent with re-orthogonalization steps in between. So in some cases it fails to converge, and by this you get like a higher, sometimes it fails, and dense ray is just more robust. So the second experiment was removing gender information. Again, same principle. So we have an embedding space we use as a like gender lexicon. The word analogy pairs male-female from the Google analogy dataset. We rotate the space such that the x-axis becomes interpretable, or one dimension becomes interpretable, and then we remove this dimension from the space. So essentially we project all the vectors to the complement of this dimension. We did only qualitative evaluation, so we looked at the similarity between occupation names and the vectors of woman and man. And if you look at the differences of the cosine similarities, which is frequently done, then we can see that in the modified space, where we remove the dimension, the differences in the cosine similarity become actually way smaller. In the last experiment, we also looked at a word analogy. We used a method, LR cos by Drotz et al. 2016, which is based on the similarity and also like a classification algorithm which classifies whether words belong to the left or right class of an analogy. And again, here actually dense ray outperforms SVM's logistic regression. The performances are all quite similar, but it shows that it's a stable method and yields reasonable results here. So to summarize, yeah, just as a reminder, like if you use rotation to make your dimensions interpretable, it never harms because nothing's changed, like the relative distances remain all the same, and it is useful. We showed that analytical solutions like SVMs or dense array yield like the best performances actually and are robust. And we have this dense array method, which is an analytic method. It's simple and it works reliably across 3 tasks. To reproduce the results, the code is also available. Yeah, I want to acknowledge obviously helpful comments by many people and happy to answer questions.
And there's time for 1 or 2 questions.
Chris Brew, Facebook AI. So you picked on the obvious examples of sentiment and gender as things which could be removed. How many dimensions do you think there are which should be removed? And how many of them can you do?
So yeah, dimensions which should be removed, I don't know. I think it heavily depends on the application. There is lexicons like concreteness or something if you want to have more interpretability. In terms of like how many you can do, so you can try to make all 300 dimensions. If you have a 300 dimensional vector space, you can try to make all of them interpretable. Obviously, if you have then the constraint that you want to have an orthogonal rotation matrix. So there is a trade-off that if you put on 300 lexicas and you want to make all of them interpretable in the embedding space, probably some of them won't be encoded very strongly because they are also correlated and they can't be correlated in an orthogonal space. Yeah.
So we are out of time, so let's take further questions offline. Thanks.
Thank you.